So we know how to solve a system of linear equations by graphing, but that's not really a very efficient method. What we'd like to be able to do is somehow put together the two pieces of information we have about our variables. For example, 3x plus 5y equals 25, and also x minus y equals 3. We'd like to somehow combine these two pieces of information in a way that will help us solve this problem. Right now, there are a lot of things that we could do. These have to be true at the same time. So we could, for example, say, well, what's 3x plus 5y plus 3? Well, 3x plus 5y is the same as 25. 3 is the same as x minus y. If these two equations are true, this one must also be true. Right? We know that. I don't think that helps us much, though. In fact, this equation kind of looks worse than either one of these two. What our goal should be is to combine our equations in such a way that whatever equation we end up with has only one variable. So, what if I told you that whenever these two equations are true, it is also the case that 8x equals 40? Well, then you'd know what to do, right? If 8x equals 40, we divide both sides by 8, and we get x equals 5. But then once we know that x equals 5, well, we know that 3 times 5 plus 5y equals 25. 15 plus 5y equals 25. How do we find y? Well, we need to get rid of this 15. 5y equals 10. We need to get rid of the 5. Y equals 2. If this part works out, we know what x and y are. 5 minus 2 equals 3, so that also works in this equation. So our main goal is going to be going from the system to an equation that looks like this, an equation that has only one variable in it. And we're going to meet two techniques for accomplishing that goal. And then we're going to talk about which technique to choose for which problems.